In this video, we're going to talk about a quality of a vector-valued function known as curvature. The notation for the curvature of a vector-valued function is denoted by, technically, it's the Greek letter kappa, but in most practical cases, we just write it as the letter k. K as a function of t for a vector-valued function, r as a function of t. Now, one thing that I want you to notice about this notation right away is that when I write the letter K or kappa, I did not put the vector over the kappa. And that is because curvature within the context of this class is a scalar quantity. Specifically, it is a scalar that's used to measure how tightly your curve is bending in space. So for example, if you have got a curve that looks maybe like this, this is a curve that is bending very tightly through space. This curve would correspond to a very large curvature and a high value of kappa. If your curve is bending more gently through space, this would correspond to a relatively low curvature. And if you're dealing with a straight line or a straight line segment is not bending at all. So this would have a curvature of 0. So curvature is a measure of how tightly your curve is bending in space. Now, one way to find curvature is to use a combination of the object's velocity, acceleration, and speed. Specifically, the curvature can be calculated by taking the cross product between velocity and acceleration, and then taking the magnitude of that cross product, and then dividing it by 3 copies of the function's speed, dividing it by the speed cubed. Now, I won't speak on why this formula works, but let's do a quick example to show that this formula produces results that make sense. Let's suppose that we're trying to find the curvature of a circle of radius r. Let us calculate the curvature using this formula and show that this formula produces results that make sense, that align with what we would expect based on how curvature is defined. So here's my prediction. If I'm dealing with a circle of a relatively small radius, a small radius circle, I predict that in this instance, I'm going to get a large curvature, a large value of k. And that's because a circle with a small radius is bending very sharply and very tightly through space. By contrast, if you have a very large circle and you have a circle with a big radius, I predict that the curvature for that circle is going to be small. So having made that prediction, let's go ahead and use this formula to calculate the curvature for a circle of radius r. And let's see that the result aligns with what we expect and what we predicted. So I'm going to start by parameterizing the circle. And to parameterize a circle of radius r, I can use r times cosine, r times sine, as we discussed in a previous lesson. Now, what I'm going to do is I'm going to take this circle and I'm going to parameterize it in 3-dimensional space. I'm going to think about this circle as it exists in 3-dimensional space instead of in 2-dimensional space. The reason why I'm going to parameterize this circle in 3-dimensional space is because this formula for the curvature involves a cross product. And I remember that the cross product is something that's only viable for a pair of three-dimensional vectors. So if I'm using this formula involving cross product, the cross product needs a three-dimensional V and A. So for that reason, I'm going to parameterize the circle in three-dimensional space, really by just putting a 0 in the z component. If I put the 0 in the z component, that will lay the circle flat in the xy plane within three-dimensional space. So this is a three-dimensional parameterization of this circle. Having now parameterized the circle within three-dimensional space, I can find the velocity vector just by doing the first derivative. So that's negative r sine of t, that's r cosine of t, and that's 0. And then I can find the acceleration by calculating another derivative of velocity. So that would be negative r cosine, negative r sine, and 0. While I'm here, I can go ahead and get the speed function, which is the magnitude of velocity, and I can calculate that in the normal way by just taking the x component of velocity, squaring that, and the y component of velocity, squaring that, and the z component, and then simplifying that result. So by Pythagorean identity, what I have here is r squared times the quantity sine squared of t plus cosine squared of t. Sine squared plus cosine is equivalent to 1. So my speed in this case is the square root of r squared, which returns a value of just r. So r is equal to the speed of this parameterization. R is equal to the p of t in this example. Next, let's go ahead and find the cross product of v of t and a of t. And to that end, I'm going to use that exact same matrix determinant method that we've used for all the cross products that we have done up to this point. I hat, j hat, k hat in the top row, and then the entries of the vector v in the second row, and then the entries of the vector a in the final row. Using the standard determinant process, I can find the results of this calculation. For example, if I think about what is the x component of this result, the x component of this result is just going to be equal to 0 because of this column of zeros on the right side. If I think about what is the y component of this cross product, I'm also going to get 0 in this case, again because of this column of zeros on the right side. And then for the z component, this is where I have to be somewhat careful. If I multiply together the products in the main diagonal and then subtract the result on the off diagonal, I get positive r squared times sine squared, and then plus, from minus negative, plus r squared cosine squared, which again can be simplified using the Pythagorean identity that z component is just r squared. So let's go ahead and find the magnitude of this result, the magnitude of this cross product is equal to the magnitude of the vector 0, 0, r squared. And that result would just be equal to r squared, since we only have length in the z component here. So we're almost done. We're almost ready to assemble the curvature. The curvature would just be equal to the magnitude of the cross product, the r squared that we just found, and then divided by the cubed speed. The cubed speed, so the cube of the r that we found earlier in this calculation. And so if we simplify this result, we find that the curvature at every single point on this circle, the curvature is equal to a constant value of 1 over r. So this makes sense, right? At the beginning of the problem, before we even got started, we predicted that a circle with a small radius would have a large curvature, and a circle with a big radius would have a small curvature. And that aligns perfectly with the result that we found down here. The curvature is equal to 1 over the radius, so this is going to give me a large result when r is small, and this is going to give me a small result when r is big. So this result coming from this formula makes sense. Now, just a note, a circle has a constant curvature, but there are certainly curves that have a curvature that varies depending upon your position on the curve. So, for example, if you have a curve that looks a little bit like this, then at this location, the curvature is going to be a bit higher because at that location, the curve is bending a bit more tightly. Whereas over here, where the sort of arc of the curve has begun to flatten out, this would be a location where k of t would return a relatively small value. So just a note, on many curves, the curvature function is not constant, and it actually varies depending on the value of t. Now, some of you may have observed that the definition of curvature seems similar or related to the definition of the normal component of acceleration, which we talked about yesterday. The curvature measures how tightly your curve is bending in space, and the normal component of acceleration measures how quickly your object moving on a curve is turning over time. So both the curvature and the normal component of acceleration are concerned with this idea of bending or turning. So what is the difference between these two quantities? Well, the normal component of acceleration is affected by the object's speed of movement. It's a measure of how fast the object is turning or bending as measured over time. So if the object is taking a relatively loose curve, but it's taking that curve at a large speed, your a sub n can be big, even if the actual curvature of the path is relatively small. So a sub n is a measure of how quickly we're turning or bending over time. It's affected by the object's speed, whereas the curvature, by contrast, is just an inherent property of the shape of the path of movement. Specifically, there's actually a mathematical equation that relates the curvature and the normal component of acceleration, which says that your curvature is equal to your normal component of acceleration divided by 2 copies of the speed. If you take the normal component of acceleration and you divide out the speed squared, then that is the same thing as the curvature at any point. So if you're working on a problem where you need to calculate both the normal component of acceleration and the curvature. This is a pretty nice formula to use to get the curvature from the normal component of acceleration pretty quickly. Let me give you an example. So I have an object moving over some curve, and its position function is given by r of t equals 2, 3t, and negative t squared. So for this function, let's go ahead and find the velocity, the acceleration, the speed, the unit tangent vector, the unit normal vector, the tangential component of acceleration, and the normal component of acceleration, and the curvature, all measured at time t equals 1. Let's basically completely describe this object's movement. So to begin with, I'll go ahead and find the velocity function, v of t, by taking the derivative of position. And so that would give me 0 in the x component, 3 in the y component, and negative 2t in the z component. Then I'll find the acceleration function by taking the first derivative of the velocity function. And so that's going to give me 0, comma 0, comma minus 2. So now, having found the velocity function and the acceleration function, I have completed all the derivatives that will ever be necessary within this entire problem. And now that all the derivatives in this entire problem have been calculated, it's safe for me to begin to plug in specific values of t. For example, the given t equals 1. So now the velocity at time 1 is equal to 0, 3, negative 2, and the acceleration at time 1 is equal to 0, 0, minus 2. From this, I can find the speed at time 1 by taking the magnitude of the velocity vector. And so the magnitude of this velocity vector would be 0 squared plus 3 squared plus negative 2 squared. So the speed at time 1 is equal to the number square root 13. From this, I can calculate my unit tangent vector, because the unit tangent vector at time 1 can be found by taking the velocity vector at time 1 and dividing out the speed at time 1, r prime divided by the magnitude of r prime. So that would be the unit vector 0, 3 over square root 13 minus 2 over square root 13. From this, I can find the tangential component of acceleration at time 1. I can find a sub t at time 1, and I can get this by taking the dot product of the acceleration vector and the tangent vector at this time. So I can go ahead and calculate the dot product of this acceleration with this unit tangent vector. That's going to give me positive 4 over square root 13. Now I can begin to work on finding the unit normal vector. And to that end, I'm going to start by taking acceleration and subtracting the portion of the acceleration vector that is parallel to t. I'm going to take the acceleration vector and subtract the tangential component times the unit tangent vector. So that gives me 0, 0, minus 2, take away 4 over root 13, times 0, 3 over root 13, negative 2 over root 13. So let me start by scaling the vector in the back, following PEMDAS and doing the multiplication first. If I distribute this scalar of 4 over root 13 to both of the entries in the back, I get 0, 0, minus 2, and then subtract 0, 12 over 13, and negative 8 over 13. Then if I do the subtraction, I get 0, negative 12 over 13, and then negative 2 plus 8 over 13. So that simplifies to negative 12 over 13 in the y component and negative 18 over 13 in the z component. Now to find the unit normal vector, I would need to take this vector and rescale it. Turn this vector into something of length 1. In order to make that process a little bit easier, I'm going to start by simplifying this vector. I'm going to rescale it just for the purposes of making it easier to work with in a subsequent step. For example, I see that this vector contains a common factor of a divided 13. So to simplify that and just make the vector easier to work with, I might multiply this guy by 13. Similarly, I might go ahead and divide this guy by 6. If I multiply this guy by 13 and I divide this guy by 6, that will rescale the vector and simplify it without changing its direction. So by applying a positive scalar multiple, this simplifies without changing direction. That's why I'm dividing by positive 6 here, as opposed, for example, to dividing by negative 6. Because if I divide by a negative scalar, that will change the direction of the vector, and so it will not point in the same direction as n anymore. So I'm just multiplying by this positive scalar as an intermediate step to simplify the vector, but I emphasize that I need to make sure that I'm multiplying by this positive number so that I don't end up accidentally changing the direction of the vector and making that direction incorrect. So now the simplified version of this vector is 0, minus 2, minus 3, and it's now much easier for me to turn this guy into a unit vector. Because it's much easier for me to calculate the length of this simplified vector, the length being, again, square root 13. And it's much easier for me now to divide this vector by its length. So I get the unit normal being the unit vector 0 divided by square root 13, negative 2 divided by square root 13, negative 3 divided by square root 13. We can do a moment of quality assurance and make sure that our normal vector is in fact perpendicular to t. You can confirm that if you dot product this n with this t, then the result of that dot product is 0. So this n and this t are perpendicular to each other. They are orthogonal to each other. So that is a little bit of an assurance that we've calculated n correctly. Now that we've calculated n, we can proceed to find the normal component of acceleration by dotting together the acceleration vector and the normal vector that we've just found. So the acceleration vector from earlier, dotted with the normal vector that we just found, returns a value of positive 6 over square root 13. So now that we have gotten all this information, we can calculate the curvature just by taking the normal component of acceleration and dividing that quantity by 2 copies of the object's speed. So take the number 6 over root 13 and divide it by 2 more copies of root 13, and we get a curvature of 6 over 13 times square root 13 at time t equals 1. If I did not have to find the normal vector, if I did not have to find the normal component of acceleration, maybe then I would have used this other formula involving the magnitude of the cross product. However, because I did have to find the normal component of acceleration anyway, I might as well use that quantity to find the curvature more easily. That concludes this video. Curvature, denoted K of t or kappa of t, is a measure of how tightly your curve is bending in space. So if you have, for example, a circle of a small radius, that's going to have a large curvature. If you have a circle of a big radius, that's going to have a low curvature. And if you have a straight line, that doesn't have any curvature at all. One way to calculate the curvature is by using a cross product. Start by taking the cross product of the velocity vector and the acceleration vector, and then take the magnitude of that result. Once you've found that magnitude, divide that quantity by the speed cubed. Alternatively, if you're in a problem where you have to calculate the normal component of acceleration, you can utilize a certain relationship between the normal component of acceleration and the curvature. The normal component of acceleration is affected by both the curvature and the object's speed of movement. To be specific, the curvature is equal to the normal component of acceleration divided by the squared speed. So if you're in a problem where you have to calculate both the normal component of acceleration and the curvature, the best formula to use is probably that one, because then you can just divide a sub n by 2 copies of the speed and get your curvature without having to do a cross product.